Hey there, welcome to this lesson on atomic Lewis structures. This is the very basics of drawing Lewis structures, and we are going to take a look at how to draw these for just atoms. They're not bonded to anything. So you're going to want a periodic table to do this, and it's important to remember that valence electrons are really the only ones that are important. They're the only ones that participate in bonding, and the number of valence electrons is going to determine the behavior of atoms as they're looking to make bonds. All of the elements in group 1 are going to have just one valence electron. All of the elements in group 2 will have two valence electrons. These elements from 3 to 12 don't behave very nicely. The number of electrons that they have in their valence shell is not easily predicted, so we're going to skip over these for now. You can still apply these rules later, but when it comes to predicting what the Lewis structure looks like, you need more information than just the periodic table for these elements. Group 13, those elements will have 3 valence electrons. Group 14 will have 4, 15, 5, 16, 6, 17 will have 7. And then group 18 is kind of split because helium is very small. Helium will only have 2, but everything from neon down will have 8 valence electrons as members of group 18. So there are a few things to think about when we're drawing Lewis structures for elements. And I kind of have this process. It's a little silly and you won't quite see it for lithium. But what we're going to do is draw, or rather write, the element's symbol, which is for lithium, Li. The symbol just means they're letters from the periodic table. Then all we want to do is take the number of valence electrons and draw them on the symbol. So even though lithium's really easy, my strategy is to imagine that lithium is in a box, kind of like this box right here. And all you're going to do is take the number of valence electrons and draw that number of dots around the symbol. And that's it. So let's move on to one that's a little bit tougher. So taking a look at aluminum, aluminum has 13 electrons in total, but we only want to focus on the 3 valence electrons that aluminum has because it's a member of group 13. We are going to write the symbol for aluminum, and then we're going to imagine that aluminum is in a box, like that. And truthfully, electrons are negative, and they don't want to be near other electrons because they're also negative. So when we draw aluminum's 3 valence electrons, we want them on 3 separate sides of this box to say, hey, these are negative and they repel each other. And then we are going to erase this box because the box is kind of just training wheels as a tool to help us know where to put the electrons. And that would be it. Aluminum just has 3 valence electrons. You would maybe write it a little bit tighter. Like that. You could put them side, side, top. You can do side, side, bottom. You can do top, bottom, right. It doesn't really matter as long as those electrons are on separate sides of that imaginary box. Now, boron is also a member of group 13, so it will also have 3 valence electrons. So we'll just write the B for boron, and then we will write those dots around boron. And you should notice that elements that are in the same group on the periodic table really look similar, and that's on purpose. Members of the same group are going to have really the same Lewis structures, and that's because they have the same properties. They both have 3 valence electrons, and those 3 valence electrons are really going to dictate how they react with other elements, which you will see moving forward in these practice videos. Silicon will have its symbol Si, and it is a member of group 4, so it will have 4 valence electrons. If you like, you can put this in the little imaginary box. You don't have to. I call it the training wheels. And then you're going to take those 4 valence electrons that it has, because it's a member of group 4, and put them on their own side of the box. And then we can erase the training wheels. And then we will have our Lewis structure for silicon. Beryllium is Be, and it is right here in group 2, so it'll only have 2 valence electrons. Typically what we do is we start at the top and then move to the right, just because that's the way a clock works. But you could also, and it kind of depends on like if you're drawing this bonded to other things, if you were drawing in a particular space on a sheet of paper. Sometimes my Lewis structures go side to side, depending on the amount of space that I have. Sometimes they're vertical. It really depends. But all of these are correct Lewis structures. It just matters that the electrons are on different sides of that imaginary box. And now you may be asking, what happens when we have more than 4 electrons? Because, there's only 4 sides to a box. Argon has 8 valence electrons because it's a member of group 18. So when we do this, we're going to draw the imaginary box for this one. The way I like to do this is to count and hit different sides of the box as I go. So argon should have 8 valence electrons. Here's 1, 2, 3, 4, 5, 6, 7, 8. This relates to Hund's rule, which you may have learned about. Hund's rule indicates that electrons are not going to double up or get anywhere near each other if they don't have to. This is more so related to electron configuration, which you will learn here in a future video. I can, of course, link that lesson below if you're interested. Hund's rule says that electrons don't double up unless they have to, which is why it's important for our Lewis structures to kind of emulate that fact. So if we are looking at, let's go back to boron. Boron had those 3 valence electrons, right? I would not want to do this because this Lewis structure is indicating that this electron wants to be close to this guy. Meanwhile, there's a place for him right here and right there. So that's why that's an incorrect Lewis structure. And that's why in this process of drawing argon, I went around the box once and then around the box a second time to make sure that my electrons were separated from each other. Now, when you have 8 valence electrons, it doesn't quite make sense. So I'll show you another one where it will click a little. The final Lewis structure for this video is going to be for sulfur. And sulfur is right underneath oxygen in group 16. So it will have 6 valence electrons. And I'm going to write the symbol for sulfur. Put sulfur in the imaginary box. And then I am going to draw my dots. I have 1, 2, 3, 4, 5, and 6. And I can assure you that this is actually the best way to draw a sulfur Lewis structure, is to put the 2 pairs side by side and then the 2 singles side by side. This is because oxygen will have the same layout for its Lewis structure. It will have oxygen like this, and then you'll have 1, 2, 3, 4, 5, and 6. So when you get deeper into this, oxygen loves to bond with hydrogen. I don't know if you know this. This is the bonded Lewis structure for water. These 2 electrons right here will turn into a single bond, and those 2 electrons right there will turn into a single bond. And drawing it this way with that imaginary box and going around the box twice will help you to get pictures like this that are more accurate than some other pictures that you'll come across later. Like this, technically, is a correct Lewis structure for water, but water really looks more like this. So if you use that box strategy, even if you just imagine it and don't actually draw it and then erase it, you're going to wind up with more accurate pictures that are going to help you later on in the course. So even though it seems a little bit silly, I would go with it. Okay, if there's any questions on atomic Lewis structures, please, of course, leave them in the comment section below the video. Subscribe so you don't miss our next practice session, and I'll see you there. Bye.